10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1. And liftoff of OSIRIS-REx, its 7-year mission to boldly go to the asteroid Bennu and back.
Welcome to the OSIRIS-REx live stream at the U.S. Space and Rocket Center here in Huntsville, Alabama, sponsored by NASA's Planetary Missions Program at Marshall Space Flight Center. I'm Joseph Vick, the U.S. Space and Rocket Center's Museum Education Director. Tonight, journey with us as we travel more than 200 million miles to the asteroid Bennu, where the OSIRIS-REx spacecraft will soon tag the surface and acquire a sample of the asteroid to bring back for study on Earth, completing NASA's most ambitious sample return since the Apollo program. Join the staff of the Rocket Center's Intuitive Planetarium, NASA subject matter experts, and myself as we embark on this otherworldly exploration with you. Together, we will examine the OSIRIS-REx mission and look at everything from launch to a simulation of the sample acquisition.
Hello, my name is David Weigel, and I'm the Intuitive Planetarium Director here at the U.S. Space and Rocket Center. And I'm very excited to be with you today to talk about all things Bennu, OSIRIS-REx, and the very exciting upcoming tag that is happening on October 20th, which is this coming Tuesday. To join me this evening to help take you through the events that are upcoming, we have a couple of our planetarium specialists, Aaron and Paul, and they will be telling us about different specific aspects of the mission and the asteroid. Now, I do also want to thank a variety of different people for making this possible, most specifically NASA's Planetary Missions Program here at the Marshall Space Flight Center. And today we will be using the software Digistar, our planetarium software, to bring you these various visualizations. So to jump right in, if you're looking at this large hulking rock thinking a variety of different questions like, what even is this behemoth in space? What is this mission OSIRIS-REx all about? Why are we going to a world like this? Why are we going to attempt to actually acquire a sample and then bring it back to the Earth? And maybe even, what is an asteroid in the first place? Hopefully we have all of these answers to all of these questions and more for you today. And really, to jump right in about Bennu specifically, Bennu is an asteroid that is not particularly large by any means. It's about 500 meters across. It's situated in the asteroid belt, and visiting an asteroid like Bennu gives us a better understanding of a plethora of different things, most importantly, how the Earth came to be, because these asteroids are the basic building blocks of the solar system, and also allows us to get a better understanding of safety for the Earth, because things such as Bennu are potentially hazardous to the Earth, not necessarily in the very near future, but potentially further along down the road. And so by visiting something like the asteroid Bennu, we can learn a lot more about asteroids in general and help to protect ourselves for the future. So I want to also answer the question, what is an asteroid in the first place? And I already said that these asteroids are the basic building blocks of our solar system, but let's take a little bit closer of a look in here. So a long time ago, some 4+ billion years ago, our solar system started out as a nebula, a cloud of gas and dust. And through mutual self-gravitation, these various gas particles started to clump together more and more and more and more. Bigger clumps formed bigger and bigger and bigger clumps, and eventually that produced a good bit of gravitational heat. And the result of this heat, once enough, allowed for nuclear fusion to occur and a star to be born, the sun. Now, that initial stellar wind pushed off the remaining material that did not clump into that star. And these different sort of protoplanetary objects smacked around in a very, very violent early solar system and eventually formed the planets themselves. Now, these planets in turn, these large objects in our solar system, gravitationally dominated the solar system in a very chaotic early solar system. And so some of these other building blocks that didn't form into planets were then either gravitationally ejected from our solar system or were shepherded into various different locales in the solar system. So the rockier worlds ended up situated in the asteroid belt, these smaller rocky bodies. And icy bodies were sort of collected more towards the outskirts of the solar system in what's known as the Kuiper belt. So the asteroid belt is that collection of dots that you can see there in the middle of the screen that is situated between the orbits of Mars and of Jupiter. The Kuiper belt, which is home to these icy bodies known as comets, are situated past Neptune's orbit. That's that last line you can see sort of furthest away from the sun at the center of our solar system. So again, in studying asteroids and also comets, we get a better understanding of these basic building blocks of the solar system, and these are really in pristine condition because they are unaffected by the same processes that we see on the Earth, like weathering, for example, and a variety of different things. And so taking these samples is something that is of great interest to us, and hence we have the OSIRIS-REx mission, even among others. I think it's a good time to take a look at how asteroids are categorized, and so I'm going to turn it over to Joseph Vick to tell us a little bit more.
Hello! I wanted to show you a fun way to distinguish the differences in space rock types using candy bars. All asteroids and space rocks are grouped into three main types, all according to what they're made of: C-type, S-type, and M-type. C-type asteroids are mostly made of carbon. We are all made of carbon too. See, the inside of this sample is filled with consistent carbon-rich material. Now here's an example image of a real space rock to compare. S-type asteroids are mostly made of stony, silicon, and iron-rich materials. See, the inside of this sample is filled with spotted, stony-rich material. Here's an example of a real S-type space rock to compare. M-type asteroids are mostly made of iron and nickel and are very dense, heavy, and magnetic. See, the inside of this sample is filled with dense, solid, metal-rich material. Here's an example image of a real M-type space rock to compare. Now, back to you, David.
So now that we have an idea of the different asteroid classifications, let's take a look at a few different asteroid options that we have actually observed. So the first visual I showed you was a simulation of the early formation of our solar system. But this look that we're seeing right now is a little bit more present day. And you can see all sorts of dots scattered in the asteroid belt, again, between Mars and Jupiter. We have observed perhaps hundreds of thousands of unique asteroids from the Earth, but we only have really good imagery for a select few. The largest thing in our solar system is known as Ceres, which was originally classified as a planet, was reclassified as an asteroid, and is now reclassified again as a dwarf planet. It is so large that it accounts for actually the majority of the mass of the entire asteroid belt. But the largest asteroid that we see that's not Ceres is known as Vesta. And we have really great imagery for both of these from what's known as the Dawn mission, which actually visited both of these a little while ago and mapped them quite extensively. After Vesta, though, our asteroids get a good bit smaller. So you can see that Vesta is about half the size of Ceres, and most of the asteroids are a good bit smaller than Vesta. Things like Lutetia, which we just pulled up on the screen, and Ida, which is about to come into view, all of these different asteroids are, first off, quite small in the grand scheme of things compared to planets, and they're also just very, very, very dark. They're very artificially brightened on the screen for you to view right now. And so because of this, we have to send spacecraft to these different worlds in order to get the sort of maps that you're looking at on the screen right in here. So while we could pick from 100,000 asteroids, hundreds of thousands of asteroids to show you, we only have a select few that we actually really know what the surface looks like. So this is a further reason for us to send a mission to something like Bennu to give us a greater sample size of asteroids that we've observed. Now, Ryugu, which just popped up, is similar in look to Bennu. It's a little bit bigger, and it's actually just was visited by what's known as the Hayabusa 2 mission from the Japanese Space Agency, and that was also a sample collection and return mission. So the idea behind Hayabusa 2 and OSIRIS-REx is to visit these different asteroids and scoop up some material and bring it back to Earth for analysis, which is an incredible thing because anytime that we take measurements from a spacecraft in situ, literally we bring the instruments to a world and we do the science there, we can learn all sorts of exciting things, but it's a completely different scenario when you have a whole world's worth of instruments at your disposal and also a greater time span to do this experimentation within. So really the sky is not the limit in this regard once we bring these samples back. We'll also be able to compare and contrast between samples from Ryugu and Bennu, and that's a very exciting partnership that's going to be forged here soon. Now, asteroids are these basic building blocks of the solar system like I keep talking about, but they're only really half of that. We have asteroids, which are the sort of rockier than they are icy building blocks, and the others are the comets, which reside in the Kuiper Belt, and they are icier than they are rocky. And if that sounds like a pretty gray thing, it is. So let's take a look at a comet. We are going to visit what's known as 67P Churyumov-Gerasimenko, and that is quite the name. You can see it in here, and I'm going to take control here and fly live for a moment. What you'll notice with this is that the screen is really, really washed out as we're looking at the nucleus of this world, which actually kind of looks a bit like a rubber duck, which is interesting and a little bit coincidental. But the reason the screen is fairly washed out is because comets, as they approach the sun, have what is known as a coma. And the coma is the result of this icy world getting closer to the sun, and heat from the sun causes the ices of the comet to sublimate, which means that this water ice goes straight from a solid into a gas, skipping the melting, and forms this sort of haze around the comet nucleus. And that ends up looking something like this. So you may have recognized Comet Neowise this summer. If you live in the northern hemisphere, we had some pretty amazing views of this, and we're able to get some great pictures. And comets are really pretty to take a look at like that. However, we aren't able to identify what the center nucleus looks like unless we get really up close and personal. And so as I sort of zoom around this a bit to give you a closer look, we're able to better understand this one because of a mission called Rosetta, which orbited this for some time and mapped the surface. But the point is that comets and asteroids were these basic building blocks of the solar system. Comets are icier than they are rocky. Asteroids are rockier than they are icy. They typically reside in these two separate locales of the solar system, asteroids in the asteroid belt, comets in the Kuiper Belt, and both of these things are crucial to understanding our origins. So, to give you an idea of how Bennu compares to 67P, you can see in here, to scale comparison, and Bennu at about 500 meters across is a good bit smaller than 67P, which long ways is about 4 kilometers across. Interestingly though, they have similar masses, and so their force of gravity is about the same on the surface for each, which is about 1/100,000th that of the Earth. I'll say that again, 1/100,000th the gravity that we would experience on the Earth. So these are incredibly, incredibly small worlds by comparison, and certainly worth further explanation. So let's jump over now to our friends at NASA to get a better understanding of some of the mission objectives for the OSIRIS-REx spacecraft.
What is the overall expectation or goal of the OSIRIS-REx mission?
So the overall goal of the OSIRIS-REx mission is to bring back a pristine sample of the asteroid Bennu. And the reason that it needs to be pristine is because as asteroids come down and, as they break off and come through the atmosphere, they burn up, they change, their composition changes, some things happen. So by bringing back a sample that has never been through the Earth's atmosphere, we're going to be able to analyze it and determine what it's like on the actual surface.
We really haven't studied an asteroid like Bennu before. We believe that the material that's on the surface is very carbon rich and not material that would survive entry through the atmosphere like if it were to come in as a meteorite. So there's nothing in the current meteorite collection that even comes close to this material that we are likely to get back, this pristine material that dates to the early formation of the solar system.
We're interested in organic rich, carbon rich asteroids because we want to understand if these kinds of materials delivered the seeds of life to the early Earth, and maybe be the reason that Earth is a habitable planet and why we're here today. Bennu also is a potentially hazardous asteroid with a non-negligible chance of impacting the Earth. And so we really wanted to understand the forces that determine its orbital evolution through the solar system.
By orbiting Bennu for over 2 years, precisely tracking it, and by all of these observations of Bennu, we will be able to much more precisely predict Bennu's position into the future and determine what the real risk to the Earth is from not just Bennu specifically, but other objects like it.
We have been doing remote sensing in terms of understanding the resources that may be available for NASA missions in the future, and understanding if there's resources available that we could use to get further in the solar system. So we really are exploring our past and understanding how we can secure our future. And that is one of the major objectives of OSIRIS-REx, as well as the great scientific value that we're bringing to the table.
Good evening, my name is Erin, and I'm going to be giving you guys a tour of the OSIRIS-REx spacecraft and its various systems and science instruments, so you can get an idea of how it's going to complete its objectives. So when I think of spacecraft, I often think of them as small things that you could hold in your hands, maybe the size of like a packing or even a moving box. But most spacecraft are not that small. OSIRIS-REx is 8 feet by 8 feet by 10 feet. And if you include the 2 solar panels, it is almost 20 feet across from wingtip to wingtip. So let's go ahead and dive into all of these science instruments. It has 5 different science instruments. The first one we're going to look at are going to be the camera suite. It has 3 different cameras in this suite. The first one is the Polycam. Now the Polycam is an 8-inch telescope, and it was actually the first camera to get a view of Bennu as OSIRIS-REx approached it. Since it's getting that early view, it was able to help with navigation as the spacecraft approached Bennu. Now that OSIRIS-REx is actually there, it's mapping the surface of Bennu in high resolution. Our next camera we're looking at is going to be the map cam. It's the one circled in green there, the little one near the bottom. Now this camera, as the name implies, is actually mapping the surface of Bennu. It's got a color wheel on it, or a filter wheel I should say, so that it can map the surface of Bennu in full color. It was also looking for any outgassing or satellites of Bennu, which it hasn't found any. The last camera in this suite is the SAM-CAM. This is for a close look at Bennu. It's a wide angle camera, kind of giving it a nice wide view of the surface of Bennu. It also has a filter wheel on it, so right after the tag event, if there's any dust or gas kicked up and blocking that camera, it can quickly reacquire vision. Going with these cameras is OLA. This is the laser altimeter. Now it is a LiDAR. A LiDAR is very similar to a radar, but instead of using radio waves to detect height, it's going to be using light waves. So it shoots a laser beam down to the surface of Bennu, and then based on how long it takes that light to reflect off of Bennu and get back to the spacecraft, we can get an idea of the topography, how high any boulders or rocks on Bennu are. The next three instruments we're going to be looking at are all spectrometers. Now, spectrometer splits light up into its different components, similar to how a prism splits up light into a rainbow. By analyzing that light, we can actually get an idea of the different chemicals and elements that are on the surface of Bennu. This first one here is called the thermal emission spectrometer. It's looking at light in the infrared part of the spectrum. So we're getting an idea not only of some of the elements, but also of the temperatures on Bennu and how that they can change from day to day or even throughout Bennu's day. Our next one, oops, I've also clicked that. Our next one is going to be the visual and infrared, the visible and infrared spectrometer. This is looking at a slightly different wavelength than the OTS spectrometer. And it's going to be mapping the surface of Bennu and getting an idea of the different elements and providing global maps of those elements and chemicals across the surface of Bennu and also at the individual potential sample sites. REXIS is the last of these spectrometers that we're looking at. It's looking at the X-ray part of the spectrum, and this one's kind of cool because it's actually a collaboration between students and faculty at the universities of MIT and Harvard. So I think that's kind of cool. So with all these instruments, we can, or OSIRIS-REx can map the surface and get an idea of the chemical makeup and select a tag site. How does it actually go about getting that sample? Well, it's going to be using the tag SAM, the touch and go sample acquisition mechanism. It has an articulated arm with that sample mechanism at the very end. And I'm not really going to tell you much more about that because we're going to have a lot about this later in our show. The last instrument I'm going to tell you guys about is the sample return capsule. This is actually the only part of the spacecraft that is going to be coming back to Earth. So the sample is going to go inside of that capsule, and then it has a heat shield and a parachute so it can safely re-enter Earth's atmosphere and make it all the way back down to us. So here is the OSIRIS-REx spacecraft. We've learned all about it. Next, it's all ready to launch.
Thank you very much, Aaron. And it's about time for us to have liftoff of the OSIRIS-REx mission. So this mission was launched on September 8th of 2016, and it launched aboard an Atlas V rocket. And this rocket allowed it to journey away from the Earth, of course, into low Earth orbit, and then prepare itself for various cruise phase as it journeyed on its way to Bennu. And what you're seeing right now is the actual deployment of the satellite itself. This is live or real footage of that. And this right in here is a simulated view of it flying over the Earth for its cruise phase. On September 22nd of 2017, about a year later, it actually came back around in orbit towards the Earth to do a gravitational flyby and redirect over the south pole of the Earth. It allowed us to take different images of the Earth and test out some of the systems. But also, it allowed this redirect, like I said, in order to sort of change the orbital inclination with respect to the solar system so that it could be on target to Bennu. Then, on its way, it imaged the different areas that we were looking for Bennu in, and in mapping that part of the sky, Bennu is exactly where we expected it to be, which seems like a, I would hope so, sort of scenario. But this sort of asteroid is so small, so hard to see, that really high precision is hard to have unless we're close. And again, it was exactly where we expected it, so that's really, really good. So it arrived at Bennu for its approach in August of 2018 and then started to map the surface. So we're going to hear now more about the mission, and I'll turn it back over to NASA.
So why was Bennu, out of all the others, chosen?
Our first criteria was accessibility. And Bennu was relatively easy to get to in the amount of time that we could get to the asteroid. That then got us to a smaller number of possibilities, and then we needed to look at the size. So size was also another factor, and Bennu's about 500 meters in diameter, so it was of a size that fit the bill for that.
Bennu is the smallest object that's ever been orbited by a spacecraft. In fact, the OSIRIS-REx team was given a Guinness World Record for the smallest orbit ever achieved and the smallest body ever to be orbited. But the fact that Bennu is so small and has so little mass, its gravitational pull on the spacecraft is just extremely tiny. The gravitation of Bennu is just about 1 order of magnitude larger than the solar radiation pressure. So it's on kind of that same order of magnitude of the sun's, the pressure from the sun's rays. And that means that there's many other forces that are really significant that we have to model carefully.
And then the final determination was the composition.
From the analysis we've been able to do from Earth telescopes and space telescopes and observing it, it appeared to have carbonaceous type regolith material on it. It also looked like it could have some water-bearing clays and some other material that could be similar to how life started on Earth or rocks that we would have here on Earth in the beginning of time.
Subsequently, as we've done our remote sensing, while we have been in close proximity of Bennu, we actually have confirmed that it does have high carbon signatures. So it should give us a real good look in time in the time capsule of what was happening in the early days of the solar system and how perhaps the seeds of life were brought to Earth.
Out of all of these choices, it's really exciting that Bennu was the one that was chosen, because now that we've arrived at this world and begun to map it to incredible resolution, we've discovered so very many things. So as it was arriving, we had done some different thermal scans from the Earth, and we realized that with Bennu's orbital period, or rather rotational period, of about 4 hours, that means that it rotates once on its axis every 4 hours. And so you have a daytime that gets very, very hot in direct sunlight and a nighttime that gets very, very cold. And this is something that gave us an idea that the surface was probably quite sandy, because sand holds on to its temperature, its heat, not very well. And so again, we expected this pretty sandy world. Well, upon arriving, you can see that this place is very different than a sandy world, and let's get an even closer look at what this looks like. So the spacecraft, upon arrival, noticed something a good bit different, a good bit extremely rocky. This asteroid is absolutely littered with boulders all over it. And, you know, for something that's supposed to be a sample return mission, this posed quite the difficulty, because if you're looking at a spot where you might land and do so safely, that's extremely hard to come by. So, you know, in order to really figure out how they were going to go about fulfilling this actual sample acquisition piece, the actual tag, touch and go event, there had to be a lot of fast thinking to determine, you know, how to do this safely. And so, without saying, they needed to map the surface quite extensively. And in August of 2018, we had the approach trajectory and the initial mapping. And then from there, starting on December 3rd of 2018, the spacecraft went into orbit around Bennu and really got a much closer look. I'm going to artificially brighten this for you a good bit so that you can see the surface a little bit better. And what we're simulating are the various orbits starting in that August 2018 timeline up until about March of this coming year, sort of into the future, March of 2021. You can see that some of these orbits, particularly those in yellow on the screen, are rather close to the surface, and we're actually able to get a global map of Bennu that is of higher resolution than anything else that we have looked at in the entire solar system. which is really incredible to think about. So the resolution that we're talking here is about 5 centimeters per pixel. To give you an idea, and that's about 2 inches, so to give you an idea of what that means, if there is a cherry tomato-sized rock on the surface, we can identify exactly where it is. I mean, that's pretty incredible to think about. So with these various orbits, particularly the reconnaissance orbits, we were able to map out the surface and identify different locations of where we might want to land. There were a tremendous quantity of these different potential landing sites, and it was narrowed down extensively until they selected the specific one. More on that in just a moment. But again, some of the difficulty with this is pretty obvious. Because if you look at the surface of this world, and I've turned off all the orbits except for Reconnaissance A, which was sort of the precursor in finding these various landing sites. If you look at what just a rubble pile this is, the initial mission called for a radius of about maybe 50 meters or so of a clean landing site, and that doesn't exist anywhere on the surface. So they're having to make do with about an 8-meter radius, and this is quite an incredible feat that they're about to attempt. Part of the way that this is going to work is through a process that was developed as the mission continued on, known as natural feature tracking, NFT. And the idea is that with this incredible map that OSIRIS-REx has generated, the spacecraft is going to be able to, in the sample acquisition event, as it's descending to the surface, it's going to be mapping the surface optically with its cameras in real time, comparing that to the database it's already generated. And this will give us a better understanding of if it's on a trajectory that is fairly reasonable and at the end of the day safe. And so this is something that had to be developed in order to accommodate this world that, again, we thought was going to be very sandy and kind of gentle, I suppose you could say, and it isn't. It's very, very interesting, very, very boulder-filled, and just a little bit different. So to tell you a little bit more about some of the crazy features that we've identified on the surface, I'm going to turn it over to Paul to give you some of the geology and geography of this world.
Hi, I'm Paul, and I will be exploring the surface of Bennu with you. So let's get started. So based off of initial observations, what scientists believe they thought they saw was this relatively smooth world, with one boulder protruding off of it. Actually, if you look in the bottom right corner right now, you can see it. We thought we saw this boulder that was about 30 to 60 feet tall. But once the spacecraft OSIRIS-REx took a closer look, we were able to see that it was a very rocky world, and it's absolutely dominated by boulders. So this first boulder right here, this is called Simrig-Saxon, and this is one of 200 plus boulders on the surface. Now, like David said, this is some of the highest resolution. I mean, this is the highest resolution global map that actually exists. And like he said, if there is something the size of a candy bar on the surface, we can actually see it. That's how much detail we have here. Now, just northeast of Simrig-Saxon, we have this boulder called Rock-Saxon. And so this is actually the largest boulder on Bennu. It measures about 300 feet in length. Also, we've actually taken a look, and this is a region that is very, very rich in something called magnetite. Magnetite is a type of iron oxide, it's a type of rust, and magnetite was something used by early explorers as the early form of the magnetic compass. So it's cool to see that something like this exists on this foreign world, but also it's something we're also familiar with on the Earth. Now, as we head northeast, we're going to come across this boulder. It's very beautiful. It's one of the more darker features. This is called Gargoyle-Saxon. Most of these things, these boulders are very different, but the thing that they all have in relation is that they're all named after mythological birds. So this right here was a gargoyle, or it's named after a gargoyle, a dragon-like creature with bat-like wings, could breathe fire. Also, you hear me saying stuff like saxum. Saxum is a Latin word that translates to stone. Now, if we pass over the equator, over the equatorial ridge, we come into a region where you're going to see a crater. And this one right here is Ossipity-Saxum. It's a darker boulder in the center of your screen right now. And just to the left, there's a lighter boulder. These are both relatively similar in size, about 33 feet in diameter. What's really interesting about this place is that this is one of 3 locations that we've observed particles being ejected into space. And so that's pretty strange because typically comets are very active bodies. They're mostly made up of ice, rock, dust, things of that sort. And so when these ices are heated by the sun, they leave behind these particles and these chunks that are lost into space. Well, with asteroids, because they're mostly rocky, it was very surprising to see such activity coming from Bennu. But studying these particles, studying this very active asteroid, helps us better understand like asteroids across the solar system. Now, if we're going to talk about prominent objects, we do have to talk about this land feature right here. This is a boulder called Ben. It's very easy to say, very easy to remember, and also it's about 70 feet tall. So basically, if you had 10 Shaquille O'Neals, stacked them on top of each other, that's the height of this boulder here. This originally was actually something observed from the Earth. And now that we have this really beautiful detail, we can see it in all of its glory. Now, our last stop is this region where we see a cluster of exceptionally bright boulders. And so looking at its spectral fingerprint, we could look at the composition of this region. So when you look at a spectral fingerprint, each element has its own fingerprint. And so we actually found something called pyroxene, an igneous rock, which is a type of lava rock. And we don't think it originated here, actually. We think it came from an asteroid called Vesta, which is the largest asteroid in our solar system. And this material was transferred from Vesta to Bennu via possibly meteoroid impacts. So this is a very small world, but there's still so much to learn. And hopefully, with the OSIRIS-REx spacecraft, with this sampling, we're able to better understand its composition, hopefully better understand its evolution, and in turn, better understand ourselves. Now, speaking of sample site, it's only appropriate that we go and visit the sample site itself, Nightingale, and hopefully get some insight as to why it was selected.
Nightingale is the selected sample acquisition site found inside the crater near the North Pole of asteroid Bennu. What is the scientific significance of choosing this creation site, and what does NASA hope to find there?
So we hope to find a nice sample of the regolith material on the surface. When we originally were looking at Bennu, we thought it was more of a sandy type structure. And when we got there, we learned it's got boulders, tons of boulders, large rocks. So how do you safely navigate those rocks to get a good sample? So we did a lot of observing around the asteroid. We studied it. We came in for high altitude scans, mid altitude scans, and we also did some low altitude scans, and you can see those images. And what we were looking for was a nice spot that we could impact that also seemed to have a variety of different material that we could bring back as a sample.
So when we started our site selection campaign, we actually started with about 50 possible candidates. And we started off with our first criteria being what we call deliverability, and which of the sites would ultimately give us enough real estate, so to speak, that we could safely touch on the surface without impacting a hazard. So we winnowed that down to 4 possible candidate sites. Also, our criteria that we looked at very closely is, of those 4 candidate sites, which of the 4 candidate sites would give us the highest probability of meeting what we call our level 1 requirement of collecting a minimum of 60 grams of material. And ultimately, it came down to Nightingale had the highest probability and what we could tell the most fine-grained material available to sample.
So let's get a little bit closer to Nightingale itself. And again, this is just like it was very exciting that Bennu was selected as an asteroid. Nightingale, I think, is a very exciting site also because it has so much by way to offer with this upcoming sample acquisition. And of course, that is why it was selected. But as we start to zoom in on this, you'll notice that, I just want you to think about the complexity involved with actually selecting this site. scientists had to go through every single square centimeter of this world in order to understand, what could be the most feasible place that we actually might journey to. And so pretty much right about now, centered on your screen, is where Nightingale is situated. And you can see it's a little bit darker in the center. And this is because it's a younger portion of the surface, meaning that it was probably the site of an ancient impact, but a more recent impact than some of the other things. And this allowed for some younger material, or I guess more pristine rather, material to be brought to the surface. This is also material that is likely carbonaceous in initial spectral imaging. And this gives us very, very high hopes of approaching and achieving our goals of getting a very scientifically interesting sample. Now, in the bottom right of the screen, you can see that really large shadow being cast by a huge boulder, and that boulder is known as Mount Doom. So the spacecraft is actually, on October 20th, is going to sort of cruise above Mount Doom and then head essentially straight down onto the surface, kind of like what we're doing right now, to this Nightingale location. And it's going to attempt to essentially high-five the surface. And I want to give you an idea of what that looks like with the tag SAM itself that Aaron told you a little bit about. So this is something that's about the size of maybe a large dinner plate, and it looks something kind of like this. It's going to puff out some nitrogen gas, and in the process, it's going to stir up some of the rubble on the surface of this regolith, basically the soil on the surface here. And the hope is that this gas, this nitrogen gas, is going to, in stirring this up, this material up, will allow it to be sort of flushed into the acquisition device here. And the goal is to collect 60 grams of material, which is about 2 ounces. If we are unable to acquire that much material, then we will have to reassess. And the idea is that we can, if we have not disturbed the sample acquisition site at Nightingale, then it's something that we might be able to go back again in the future, within the next month or two, to attempt again. Or if we have disturbed the surface, then what we might do instead is visit our plan B, which is the Osprey site, and with the same goal, again, of using this nitrogen gas to sort of flush some material up into this acquisition head. It is also worth noting that this sample site in particular really gives us the best range, sort of width of safety zone, but this safety zone is still incredibly small. So if you think of the OSIRIS-REx spacecraft as something that is, about the size of maybe a 15-seater van, you're looking at trying to park this in a parking spot, from orbit, and that's pretty crazy to think about. So again, a very, very daring mission, an exciting thing as well. And let's learn a little bit more about the ins and outs of this actual tag acquisition. I'm going to turn it back over to NASA.
Could you guide us through this complex acquisition sample, the sort of engineering complexities and how it's going to come in, take the sample from Bennu?
If you look in particular at the Nightingale site, it's about 10 to 15 times smaller in area than what the spacecraft had been designed to. We originally had a 50-meter diameter landing zone, and the safe area is roughly 16 meters in diameter. And it's right around that area are large boulders, some of which are the size of a 2-story building. So we're really navigating the spacecraft into a tiny spot, and it has to be, right on target. Otherwise, it's potentially unsafe for it to touch.
Once we did get to Bennu and we realized that we were going to have to really sharpen our pencils and increase our deliverability precision, we did go ahead and switch from the LiDAR-based navigation process to natural feature tracking process.
We're really handing the keys over to the spacecraft once we leave orbit. The sequence is pre-programmed, but it's up to the spacecraft to collect these images, do the update of the final 2 maneuvers, and get down to the surface, and also just monitor things to make sure everything is within expectations and and abort if we get off course.
The OSIRIS-REx has its sample head, and it's covered with sticky, almost Velcro-like stuff for, similar to a gecko's pads, right? To help pick up material as it's impacted. On top of that, it is now mounted to an arm that's articulated, similar to your arm here. It has joints that can move, it can rotate a little bit. And so what happens is, as we approached Bennu and we were ready for sample acquisition, so it extends out its arm and it can pivot, and then it will lower it and it will come down onto the surface. And so when we actually impact the surface, colloquialism called like a fist bump on it, right? Kind of imagine it that way. So you coming down with this head and you're going to impact the surface. And when we impact the surface, it's going to touch for just a short period of time. But there are nitrogen bottles that are going to evacuate through the head. So it's going to make kind of a circular swirling of some of this particulate matter that's going to be sucked back up into the head, as well as stick to the outside on these pads. And then when the head comes back, it's going to go and it's going to do a measurement to make sure that we have enough sample. And if we have enough sample, then it's going to stow that back inside the spacecraft so it will be protected and sealed for its return back to Earth.
And so as we eagerly await this upcoming TAG Touch and Go event on October 20th, I want to walk you through what that is going to look like in a simulation we put together. So the OSIRIS-REx spacecraft really has, and its team, has been prepping for this specific moment. I mean, there are so many mission goals, but like, this is it. I mean, we want to acquire material from an asteroid, a basic building block of the solar system, to better understand its composition, better understand how we came to be on the Earth, our origins. We want to be able to predict how asteroids like Bennu orbit around the Earth, or orbit around the Sun rather, with regard to the Earth, so that we can protect ourselves. And it all comes down to this. And so as the spacecraft slowly drops essentially straight down onto the Nightingale landing site, it is going to be imaging in real time, again, like I was mentioning, using the newly developed feature tracking, natural feature tracking system. And the idea is that it's going to be comparing the landscape that it sees with its already built up data set to make sure that everything is where we expect it to be, that the spacecraft is where we expect it to be with respect to these different boulders. It's going to navigate down into the region that is the most serene, the most finely rubbly of all of these, of the entire location at Nightingale. And in particular, that articulating arm, the TAG SAM itself, again about the size of a dinner plate, is going to bump down onto the surface to allow for collection of this gravel to take a sample. So you can see as it approaches closer and closer and closer, an idea of what the spacecraft is going to see with, again, unparalleled resolution throughout the solar system, something that is an incredible result of the mission already. And as soon as it does make contact, that nitrogen gas will get pumped in, and it's almost the opposite of a vacuum effect, to where the circulation of that airflow, that nitrogen gas, will allow for this collection of the Bennu regolith. It will leave, flying basically straight back away from the asteroid for a time, so that it is sufficiently far away and safe before it tries anything. And it will test this material. It will actually sort of spin the sample to determine what its mass is, to make sure that we did indeed get the desired 60 grams. If we were able to get some material but not enough, then we may re-tag the surface in Nightingale if it is sufficiently undisturbed, or journey on to Osprey and try again to collect a little bit more sample. But if we do succeed in getting enough sample, then the TAG cameras are going to, TAG cam, is going to take a look, take a picture to make sure everything is closed and properly sealed so that we don't lose any sample, and that sample will get stored in the sample return capsule so that the spacecraft can then journey back to the Earth with this sample from the spacecraft, or from the asteroid. So, if all goes well, the plan is that OSIRIS-REx will continue orbiting around Bennu, mapping it, getting different imagery and different scientific data, and will be departing in spring of 2021, sort of early March, and then we'll have about a 2-year journey back to the Earth, returning the sample in 2023 or so. So that really brings us to the end of this presentation, and we're just eagerly awaiting the upcoming TAG, Touch and Go, for OSIRIS-REx at the asteroid Bennu. And we hope that you watch along with us and with NASA as this event unfolds. I further appreciate you joining us today and hope that you enjoyed your time with us. And I'd like to thank everyone who made this possible, my entire team, but also NASA's Planetary Missions Program at Marshall Space Flight Center for helping to sponsor this event. Lastly, remember that you can join us at the U.S. Space and Rocket Center and the Intuitive Planetarium anytime that you journey to Huntsville, Alabama, and we would love to see you here. But in the meantime, remember to stay excited and keep looking up. Thank you so very much.